welcome. Just now, we are going on another presentation. Professor Sherif is a participant of INTERM conference as an invited speaker. He's joining us from University of Manitoba, Canada. He's going to present his presentation live. His presentation title is Sparsity-based Spectral Unmixing of Hyperspectral Imaging Data using Kronecker LARS Angle Regression. Hello, Professor. How are you?
Well, hi. Good afternoon, everyone. Can you all hear me?
Good afternoon. Yes, we can hear you very clearly. Thank you.
Okay, great, great. Well, first off, I'd like to thank the organizing committee and particularly Dr. Ahmed and Dr. Banu Oral for that very kind invitation. And today I'll be talking about hyperspectral imaging, which is really a technique that is between imaging and spectroscopy in a way. And I would like to share with you some of our results on spectral unmixing techniques that we developed to make such a thing quite practical and easily doable on relatively small computers. However, I would like to share my screen. Am I allowed to do that here? Let me see. Can you see my screen now?
Yes, Professor, we can see it.
Okay, and then let me just go full screen here.
Yes. When you are ready, you can start your presentation. We are
Yes.
just now start the recording.
Okay, please do, please do. So today's talk is on sparsity-based spectral mixing of hyperspectral imaging data using Kronecker LARS Angle Regression. And this work is a recent work in my group. It's been done by my PhD student who just graduated a few months ago, Ahmed Rouaini, and myself. I'm Sherif, and I'll be the one giving this presentation. So what I'll talk about today essentially is I'm going to give a bit of a background on what hyperspectral imaging is. And as I just said earlier before the presentation, that this is a technique where we use pretty much like standard imaging, 2D wide field imaging. However, we do that using many wavelengths, which is really like colors. And that allows us to get spectroscopic information about the scene that we're imaging. I'm going to talk about unmixing, which is really how to get the spectral signature that's been acquired by hyperspectral imaging. And I'm going to talk about a technique, about a mathematical technique that we developed called Kronecker LARS Angle Regression that allows us to do that process in a very efficient way. And by efficient, I really mean it is less time consuming, and also it will not require as much or as such a big storage, computer storage, as would typically be the case for that. And I'm going to conclude and talk about some future steps that we're working on and some of the things that we've done beyond this work. So this is the section here on hyperspectral imaging. So hyperspectral imaging essentially is what you see right here is right there. This is an image, let's say from a satellite or from a plane that is taking a 2D image using one wavelength, okay? And now what hyperspectral imaging does is it uses a bunch of filters or some spectrograph where now we stack images like these 2D images, we stack them in this depth, for example. Here you have a spatial dimension, let's say Y, X, and then in this depth or Z direction, we have the same image repeated, but it has been acquired with a different color or a different wavelength. Of course, I'm saying color here very, kind of loosely because, it could very well be in a part of the spectrum that is not visible. So typically, hyperspectral is common in either the visible region or in the near infrared region, sometimes even long infrared or mid infrared region. So what happens here is if you look at any location right there, if you look at any pixel here, it's X and Y, and now the length of this pixel would become a vector, and this vector here would represent, let's say, the absorption spectrum of whatever the materials that are at this pixel, how it got, let's say, how the light got reflected back. So these are spectral signals. So here, for example, if you look at, if this happens to be pure soil, then at this location, you'll end up with the signature for the absorption of soil, or the wavelength used. Let's assume it's visible. Here it's vegetation, here it's water. Applications for hyperspectral imaging are incredibly many to list, but some of the very typical applications are remote sensing, and I would say remote sensing is a big thing, satellite imaging, all these kind of things. But there's so many small applications that are using hyperspectral imaging. So what is the unmixing problem? Maybe I should, is this sort of showing? Maybe I should take this out. So the unmixing problem in hyperspectral imaging is if we are using, let's say, cameras that are acquiring images from, let's say, from space, from satellites, or from airplanes for remote sensing, then the resolution, the spatial resolution of such cameras will be relatively low. Hence, each pixel, each spectral pixel here would be a mixture of spectra of the materials in the scene, because now we would be, let's say, imaging a meter, a few meters by a few meters on the ground from the satellite, or from a plane, or even if it's in the lab, you're trying to image something really small. You're trying to find out what are the chemical material that are present in the scene. There would be a very good chance that these materials are not they're not pure pixels in a sense. So we end up that each spectral pixel is a mixture of these materials, and these pure materials, it's part of the lingo, they're called endmembers. So what happens now is each one point here in depth is essentially, a combination of all these signals together, and they're added together in a way that we would like to know. So we would like to know, the spectral unmixing really involves, we want to estimate all the present chemical materials or endmembers. And we also would like to know their percentages in each pixel. So you say, well, this pixel is, let's say, pure water. This pixel is 70% water and 30% sand, etc., etc. So this is what we are talking about when we talk about this spectral unmixing. Okay, we typically use a linear mixture model in the sense we're saying, well, these spectra are mixed in a linear fashion. That is a good approximation. It works in most cases, but it's obviously not necessarily the most accurate. However, it ends up being more robust when we do the signal processing. So here we just look at it and say, well, this is the sunlight having all kind of wavelengths. It comes down here on these locations, location S1, S2, S3, and maybe we end up with the signal at one of these is going to be, a combination of percentage A1 of S1 plus percentage A2 of S2, percentage A3 of S3, where A's are the abundances, which are the ratios of the presence of these materials, and S1, S2, S3 are the unknown spectral signatures for materials. So now we can think of every single pixel, spectral pixel would be Y of I. It essentially is going to be that linear combination between Sj, AJI plus noise, okay? And we also need to put some other constraints. So the problem really would be, given these Ys, given these spectral pixels, we would like to figure out what are the S's that are available and what are their percentages. So obviously the percentages will have negative, they're less than 1. So you have AJI are going to be bigger than 0, and they all have to sum to 1 because there's only 100% of these materials in one pixel. So we can write this in a matrix form where Y is equal to SA, where Y is essentially the matrix that you've taken this cube, that cube right here, this cube, and we just flatten it. We just take this cube and just essentially flatten it, where we just have on the columns of this matrix just the spectral pixels. So when we do that, this is known in signal processing as a blind source separation problem. Blind source separation problem is a very generic problem, and unmixing of spectral or unmixing of hyperspectral imaging data is one special case of that, where we say we have this matrix representing these spectral pixels, and we want to factorize this matrix Y into SA, where S are the available spectra, and A are their abundances in each of these spatial locations, and E here is a noise term. So the typical task spectral imaging analysis are essentially these are like typical things that are done, like anomaly detection. As I said, if you're talking about, if you're talking about approaches to achieve this unmixing that we're trying to do. So also before we talk about the math, which I have the impression that it may not be very interesting to some people here, I'll go over the math relatively quickly, but I would like here to say a few words about if you have this cube, if you have this data and you're trying to solve for these unknown spectra of materials in this hyperspectral imaging cube, you can do it in two ways. You can do it in a supervised approach, where essentially you go on and say there are spectral library, you have a spectral library, and now you're trying to find out among these spectra, what are the ones available in your data. So this is supervised in the sense that you have some prior knowledge about what you're trying to do. And the other approach here, which is the approach that we're taking, is the unsupervised approach, where essentially you don't make any assumptions about what spectra are available or what are their abundances or ratios that they're present in each pixel. So typically, people have solved this through non-negative matrix factorization, or through solving the LASSO minimization problem, which I'm going to talk about. Now I'm going to focus on the sparsity-based hyperspectral imaging unmixing and how it is done using this sparse signal processing ideas. So the way it works is this, is like we can think of the unmixing problem. I remember here, Y are just the pixels in a matrix, where we would like to find out matrix S and matrix A that would fit this data. What we're looking at here is like we want to minimize the fit between the data and the model that we have in mind, which is the linear mixture model, where S and A are both unknown. So we want to minimize over S and A to find out what are the end members and what are the abundances. The biggest problem here is this problem is highly underdetermined, meaning it's not unique. There's so many S's and A's that could fulfill this issue. It's almost like saying 7. 7 is made of what? 5 and 2, or 3 and 4, 6 and 1. It's it's a non-unique factorization problem. So what we do here is we impose a constraint. We need to impose more constraint to make sure that we're obtaining S and A that are unique, and these are the ones that we really are looking for to fit this data Y. And we constrain this minimization problem by adding a sparsity penalty term, by saying we are assuming that these spectra that we're looking for are going to be sparse, which means they're mostly zeros. They mostly have zero values when they are represented in a particular domain or a particular linear transform. So this problem here, this minimization problem here, is a non-convex problem. And as you probably know, when it comes to the optimization world, the easy problems in optimization are convex. The non-easy problems in optimization are the non-convex problem. So here, this problem when minimizing over S and A this problem is a non-convex problem. It's hard to do. So what we do here is we do something called coordinate descent, where we fix S and optimize for A, and then fix A and optimize for S, and you keep doing this, you know, in an iteration until conversion. And the good news is when we fix S and optimize for A and fix A and optimize for S, we end up solving two convex problems where we're minimizing over S with A constant, minimizing over A with S constant. So these are two problems that are relatively easy to solve because they're convex. So the first problem is we're seeking the end members. We're looking for these spectra by solving a least squares problem with a sparsity constraint. And as I said, the sparsity constraint comes here from the idea that we need to make the solution unique. However, there's a big problem here, and this is the main difficulty that I'm about to share with you. Our solution to solve is this is a least squares problem that is, you know, straightforward least squares problem. However, it's a matrix least squares problem. It is not a vector. It's not like the AX equal B type linear system. This is a matrix linear system, not a, by that I mean, this is a matrix and this is a matrix. It's not a vector minus a vector. So this is a matrix minimization problem. This problem here is known as the LASSO problem in statistics, or known as the basis pursuit problem in the signal processing community, so to speak. The second problem here, when we're trying to minimize to get the abundances given the S that we obtain from here, we just keep going back and forth between these two problems. The second problem here is you're trying to find out A, and that this is a very standard least squares problem. Again, it is a matrix problem, but that's easy because this term is going to go because it doesn't depend on A, but this term here is S depends on S, and that makes it a bit of a more difficult problem to solve. So what we do, the way we go about this is we do put a pre-processing step. The pre-processing step is to transform the problem into a different domain using a dictionary or a representation to promote the sparsity of S, where we say S is equal to phi alpha. Here I'm going to pick up the pace a little bit because there's a bit of math that probably many people are not interested in. I'll share with you a couple of papers that we published in the last year, and 2019 and 2020, that's related to that. And now we just have this S now becomes alpha. It's the representation in phi. And now we use this as a warm start to this optimization problem. And now we also represent the data, which is the hyperspectral imaging cube in this phi, and it becomes beta, where now the problem becomes minimize alpha and A in this form. And the solution could be obtained through a coordinate descent method, as I said. And now we could use this using LARS, the least angle regression algorithm, which is a very, very powerful algorithm. But the problem with the LARS algorithm that's been developed many years ago, I would say maybe 10, 15 years ago, so is that it requires you to vectorize this problem. If you vectorize this problem, which means this is a matrix problem, you can always make it into a vectorized problem using Kronecker products, but that now you end up with a humongous matrix that you probably won't be able to store on your typical laptop or desktop computer. And after that, when you do this, you end up with solving for the abundance matrix that way. And after convergence, you just eventually just go on and get the S through an inverse transform, getting the the S from phi. Okay. One thing that we need to keep in mind here is that this minimization problem has a fitting. This is a fitting term. We're minimizing how the data fits beta, and we're also minimizing the number of coefficients in this alpha. That's the sparsity term. This alpha here is very critical because I can say if you want to have this term to be minimized, then this alpha here should be 0, and if this lambda here should be 0, and if this lambda is very high, then now you're putting a big emphasis on the sparsity, and it doesn't matter how the fitting is. So this is really the balance between your two criteria, is give me a very sparse signal that fulfills a criterion, and this alpha is balancing these this lambda, I keep saying alpha, it's lambda that does that, and this is known as a regularization parameter. And you can see here that if you want absolute sparsity, you can just take this solution right there. And if you want, the best fit, you can take the solution right here. And now this is what gets you on this Pareto curve that says the effect of lambda on this lasso minimization problem. So typical approaches to solve this lasso problem is you can go on and use something called proximal methods. And this is really, kind of easy. It's not a problem when it comes to storage, but it's very inefficient because it can only solve this problem for one single lambda. So if you want to solve this problem really properly, you'll have to solve it for many, many values of lambda and then pick the solution that you feel is the right solution. However, least angle regression is a method that allows you to solve for all values of lambda all at once. However, there's a bit of a problem here. If we want to do that, this is very inefficient because this LARS has, until our work years ago, only used for a vector least squares problem. It is not suitable for, this matrix least squares problem that we talked about, which is naturally arising from the cube of a hyperspectral imaging data. So now I'm going to talk about our work in this. Is essentially what we've done is we've taken this least angle regression and we've generalized it to be able to handle multi-channel data, which is really that least squares matrix problem. And I will show you here how that works very quickly, and I will focus on the results essentially. So the idea here is this LARS allows us to get the solution that we're looking for through building this solution from starting with a zero solution, and you build it one coefficient, one value at a time. And you keep doing this until you reach the right level of fitting, error, and sparsity that you find to be acceptable. And I'm not going to go through that. This is standard stuff. I'm not going to go through this, but this is now our method where instead of solving this matrix problem, you can solve this matrix problem with LARS by going and saying, this is a matrix problem. I can vectorize it using Kronecker products. And this vectorization really becomes, instead of a matrix least squares, it becomes a vector least squares, but now your matrix is truly, truly humongous, and it's usually quite hard to store. So what we've done is we've developed this multi-channel Kronecker LARS algorithm. It's suitable for any multi-channel data, but we applied it specifically for this. We applied it for this particular application, where now, if you have time later and you're interested, if you look at our algorithm, it does not require us at all to create this big matrix. We are always doing our implementation and our steps here without any requirement to build this humongous matrix, which would be quite impractical to do in a regular computer. So some results to show you what we're talking about here. We have some synthetic data cubes where we basically picked 3 matrices from a spectral library from NASA, and we did a mixture that we synthetically made, and we used the K-LARS, our algorithm here, to solve this basis pursuit or to the LASSO problem. And we've used quafflets, which is a special type of wavelets. We used quafflets for our pre-processing step, and we did some denoising also using wavelet, simlet in particular. And these are the results. Let's say we created that. We created that data cube as made of grass, concrete, and asphalt. And these are the estimated end members. One of them is coming from our method, from K-LARS, and the other one is coming from the other method that I told you was very inefficient because you had to do this lambda many, many times. And not only that, our method using K-LARS is very similar. It just happens to be way, way more efficient because you could do this without having to repeat the problem, let's say, I don't know, maybe 20 times or so. And even the correlations between our results and the results that we use as a ground truth from something called nFinder, they are slightly higher. This is another Okay, this is another synthetic. This is another synthetic cube between aluminum, copper, and steel. Now we've tried it on actual cubes. Obviously, this is the Moffett Field cube from NASA. We estimated the end members here from a program called EndFinder, and now these are the EndFinder, end members, and these are our estimated end members. And again, we've obtained slightly better results than the one using the older technique, but with much faster and much more convenient practical implementation. This is a practical, let's say, this is a practical cube. This is part in British Columbia in Canada. This is essentially a satellite image. And if you look here, these are the end members that are obtained. We found out the number of end members using a principal component analysis, even though there are more than one way to do it. And here you can see these are the abundance maps. So if you look at any pixel at any location here, it tells you the number of, it tells you like these three end members, and these are their percentages in that hyperspectral imaging. So conclusion, the conclusion really I'm trying to share with you today is we developed a novel least angle regression method. This novel least angle regression method allows us to use LARS in a practical way for multi-channel data. And this multi-channel data is naturally could be, like hyperspectral imaging could be naturally thought of as multi-channel data. So not only we developed this general technique, we applied it to unmixing of hyperspectral imaging cubes, and this is the paper we published in Signal Imaging Video Processing last year. We successfully applied it to both actual and synthetic hyperspectral imaging data cube. As a future work, and actually we are working on this right now, is we're trying to extend this method to be dynamic, because it's very typical for hyperspectral imaging to not just be taken that way, as in like one wide field and another. It's like it's usually done through scanning. It's done through scanning, whether because of the satellite or the plane or whatever that you're doing. There's also a newer or like a more favorite technology now called the push broom technology, where it really images one line and another and another and another. So we are developing, or like we're extending our method to be dynamic, in the sense that you can do this unmixing in an even further, more efficient way by solving one problem. When you go to the next line, you don't have to start from scratch. You're just updating these results as you scan through the data. And actually, this is the most generalization for our Kronecker LARS. We developed something we call tensor LARS, or tensor least angle regression, that it sparsely represent multi-dimension signals. Multi-dimension signals here would be not just matrix equations, but it could be 10 dimension, 15 dimension. And we published only like, I don't know, maybe a month or last month, actually, it appeared in Neural Computing. And this is something that could be used if, let's say, you're interested in this type of spectroscopic information in time, or you have any other dimensions that you want to incorporate in your data. And with that, I would like to welcome any questions, and thank you for your attention. Thank you.
Thank you, Professor. This very interesting and very nice presentation, and very interesting research. Thank you. Is there any question? If there is a question, you can write the chat section.
I'm trying to stop sharing, so.
Yes. You can stop the sharing.
Yeah. So, okay, yeah. Okay.
If there's no question, after the conference, do you want to ask any question to Professor Sherif, you can send him an email. Thank you, Professor, again. for the
Sure, thank you very much.
participants,
Thank you.
of our virtual congress. Thank you so much.
Thank you. Appreciate it. Thank you.